physics-guided machine learning. I will start telling you about why we are doing this before I present the case we are looking into. Then I will go into how we are modeling the system, and in the end I will show you some results and some concluding remarks. I'm not going to spend much time on this slide because we all know that the marine industry is going into a phase where we have to reduce CO2 emissions by a lot. And this can be done in many ways, and for this particular case we are looking into efficient voyage planning and especially weather routing. I will assume you all know what weather routing is, and this weather routing is typically done on a large scale, typically crossing the Atlantic. But what we have done here is to look into this for short sea cases. On the right hand side you can see this is a fjord in Norway. That has some electrical ferries crossing it. The distance here, it takes about 30 minutes to cross it, and there are multiple vessels traveling back and forth here, so that's why you see that the paths here are separated with some safety distance. But even though this is just a small trip, we do see that there's a lot of different paths that's been chosen, and this is just for one day. So that gives motivation that, well, it could be that it is possible to just do small modifications in course and speed to optimize the path. What's more, we have only focused in the transit phase for now. And it turns out that 80% about the consumption goes into the transit phase for this case. Where we equipped a vessel that's logging a lot of data. It's logging at 1 Hertz, and it's logging electrical power, thruster both at the front and back of the vessel, GPS position, and it's equipped with a wind sensor and some draft radars to measure the draft of the vessel. I can also use the draft radars to measure the trim angle. From met.no we get weather information with a resolution of 800 times 800 and a time resolution of 1 hour. From met.no we get information about current and waves. This is how we're modeling the system. We have a data collection phase here where we store all this data into a database. And all this data is then used to train the energy model. And once the energy model is trained, we can use it in the optimization part of the problem given here. But I will start with the modeling phase. We have proposed 2 different energy models. The first one is a linear regression model with the parameters as you can see here. The reason for choosing these parameters are well explained in the paper, but the idea is to separate them or define the parameters such that they're independent on each other. The second model is a hybrid physics-based model, and the idea behind this model is that, well, since we already know some of the relationships for vessels and how they behave with incoming forces, why shouldn't we use that knowledge? So that's why we have added known relationships for current and wind forces. In addition, we've also added a non-linear term that might, since we know that speed is usually given in this form of squared. To test how these two models are performing, we have used about 1,000 trips going back and forth with the vessel, and divided these 1,000 trips into a set with training trips used to train the model, and a smaller set with the testing trips to test how accurate the model is. What we get out of this is that for the linear case, we get a test error of about 5.4%, which is quite good. But we show that the hybrid model is even better, with only a test error of 4.7%. What is also important to show here is that the difference between the training errors and the test errors are quite small, which indicates that we do not see any sign of overfitting in this case. Finally, we should also notice that, for instance, the 4.7% error here is significantly better than what we presented during the Compit paper in 2021, where we showed a test error of about 77%. So that's quite an improvement since that paper. It is also interesting to see how the different parameters are weighted for the two different models. On the left-hand side, you see the linear model parameters, and on the right-hand side, you see the hybrid model. I'm not going to go into details too much here, but what is, for instance, it's quite interesting to see that the linear model picks up the transversal current velocity as the most important parameters, which doesn't really make sense in a physical point of view. So in general, the hybrid model is much more intuitive when it comes to physical relationships. In addition to previously presented, it gives a better performance. So, given that we have the energy model, we can then use it in the optimization phase. And we have done that, and just a random trip, we showed that with small changes to speed and course, we could get a 3.7 energy reduction. And what is important to highlight here is that we're actually going a bit longer route than the original one. And even though it's longer, we still reduce the consumption with 3.7%. So that shows that this is weather routing in practice. So, to summarize, for those of you who are interested in the details in this paper, I would refer you to the reading the paper itself. For the rest of you, I would like to, at least if that you should remember one thing, and that is this take-home message presented here, that if you include physics into the machine learning model, it improves both accuracy and the understanding of the model. And finally, I would like to thank our project partners, Norwegian Electric Systems and Hav Design, in addition to the Research Council of Norway. Without their support, this work couldn't have been done, so I'm greatly thankful for that. Thank you. Thank you.
Thank you. Hi. Hello, hello. Can you hear us? Hello?
Yes, I can hear you.
Hi. Thanks for joining us online. Now, any questions from anyone? And also, online participants, you're welcome to key in your questions in Pigeonhole as well. It's a very interesting topic. I think machine learning is increasingly used in many applications. I think it's very interesting to know that it's also used in your research on route optimization. A question?
Okay,
Yeah.
Okay, thank you for the interesting presentation. Actually, it's quite interesting to know that by changing the route a little bit, then you can have a 3.7% of energy saving. And my question to you is that I noticed you are using a electrical vessel, right? So I wonder if, let's say, you are using the traditional fueled vessel, like the marine gas oil or HVO driven vessel, then what will be the difference in the result as compared with the electrical driven vessel? Yeah.
That's a good question. We haven't looked into that at all, so it's a bit hard for me to answer exactly on that. But I do believe that there will be some changes, but that's just personal opinions. Perhaps not as much as for electrical Paris studies. So that's just my personal opinion.
Thanks. Any questions? Or anything to add or any comments? No? Okay. So then, thank you very much for joining us. And then you may please also stay on for some other presentations as well. Thank you, Ulrik. Thank you.